This is section 2.3, product and quotient rules and higher order derivatives. So learning a couple more derivative rules today. The first one is the product rule. So if you have a one function times another function, take the derivative. You take the first times the derivative of the second, plus the second times the derivative of the first. And then there is a rule for three functions, but we're not going to worry about that one so much right now. So to find the derivative of this first one, so let's look at h of x. So our first function is 3x minus 2x squared. And our derivative of our first function is going to be 3 minus 4x. Our second function is that 5 plus 4x. And the derivative of the second one is just 4. So we have to take 1d2 plus 2d1. So in this case, h prime of x is equal to 1 d2 plus 2 and then d1. And then we just simplify. So here's 12x minus 8x squared plus 12 plus 12x minus 16x is minus 4x. And then minus 16x squared. Combine like terms, negative 24x squared plus 8x plus 12. And we are done. All right, let's look at the second one. All right, so the second one, the first function is 3x squared. So d1 is going to be 6x. Our second function is sine of x. And d2, sine goes to cosine of x. So y prime is going to equal 1 d2 plus 2 d1, and I like to put that x out in front. And then we're done. And for that last example, you can try that one on your own using the rule for three functions. The quotient rule is low d high minus high d low over low squared. So let's take a look at what that will be like. So for the first one, y prime equals our low, so x squared plus 1, d high, which is just 5, minus high, 5x minus 2, d low, which is 2x, all over the quantity of the low, so x squared plus 1 squared. And then we're just going to simplify. So x squared plus 1 times 5, here we go. So we have 5x squared plus 5 minus 10x plus 4x. Actually, that's 10x squared all over x squared plus 1 squared. And we should get negative 5x squared plus 4x plus 5 all over x squared plus 1 squared. And then we have some more trig derivatives to talk about today. So the derivative of tangent is secant squared. The derivative of secant is secant tangent. The derivative of cotangent is negative cosecant squared. And the derivative of cosecant is negative cosecant times cotangent. And then higher order derivatives. So the first derivative we've done. The second derivative is just the derivative of the first derivative, the third derivative, the fourth derivative, so on and so forth until the nth derivative. These are just different ways we can denote various derivatives. So I would say the most common are going to be those first three columns. So y prime, y double prime, y triple prime, f prime, f double prime, f triple prime, and then the dy dx, d squared y, dx squared, d cubed y, dx cubed. Really, we're only going to focus on the first, second, and third derivatives. So an application of higher order derivatives is used a lot in physics. So if we have a position function, f of x, the first derivative is going to give us our velocity function. The second derivative is going to give us our acceleration function. And the third derivative is going to give us the jerk function. We really don't talk about the jerk very much, so we're going to focus on velocity and acceleration. So because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects is given by s of t equals negative 0.81 t squared plus 2, where s of t is the height in meters and t is the time in seconds. Find the velocity and acceleration functions. So first, let's find the velocity function. And we know velocity, v of t, is equal to the position function, the derivative of it. So s prime of t. So the derivative of that should be negative 1.62 t. And then the acceleration function is equal to the derivative of the velocity, which is the second derivative of the position, which is just negative 1.62.